Meeting is being recorded.
Who has spent the last 15 years at Roche in process R&D and has been leading work in high throughput experimentation for the last 6 years. And joining him is Vera Jost, who trained at Roche and holds a bachelor's degree from the University of Basel and now works alongside Georg in HTE. In this session, they'll explore smart ways to design experiments and how HTE can go beyond simple reaction optimization to deliver deeper chemical insights. And with that, I will hand over to you both.
Thank you very much. Thank you very much also for the kind introduction and for inviting us. So Vera and I, we are both process chemists at heart. So we got only assigned to being HTE chemists, and so we always remember or try to remember what it feels like to be on the other side as customer. And like that, close to our heart is really to make whatever we do, useful for the people in the lab and not to just run plates for the sake of plates. And so we have provided a little presentation for you that is very much focused on process chemistry and what HTE can do for process chemistry, and also to maybe also send you off on your way with some tips and tricks dealing with HTE and HTE results. And I'll start off with a problem. I'm very sorry. Our patent lawyer, did some work to the structures so that they're not too obvious anymore. But basically, it's about how to prepare this coumarine type structure. And you have stereogenic centers, you have some functionality in there, and you had a medchem route that was, let's say, long and creative, but not very scale-up friendly, with lots of weird bond disconnections and stuff. And so we had to come up with a completely new route. And in that completely new route, we envisaged, say, like, okay, maybe we can introduce these two stereogenic centers by doing some kind of reduction, hydrogenation, and then make that using either CH activation or some kind of Heck type chemistry, addition and then cyclization. And when you then look in the literature for this particular reaction, you see like, oh, there are many, many examples. Pretty much every transition metal you throw at it will be able to do it. And there are many good yielding examples. So why would you need HT for a reaction like that? But problem, often you need stoichiometric silver or copper as an oxidant. So we're talking here about the reaction where the substituent here is an H. You had also a suspicious lack of precedent for electron-poor aromatics. And as you can imagine, these A's here are there for a reason. So there was at least one nitrogen in that ring. And as you can imagine, as long as this is not symmetric, so say here there was a second flanking hydrogen, poor regiselectivity was observed because the differentiating power between those two hydrogens often was poor. So what do? Well, you start screening and you look at precedent. And this was the first plate that we came up with. Let's say we have a creative way of designing plates. So we pretty much throw everything at that first plate that comes out of SciFinder. And we will even throw stuff on there that will never ever fly in a reactor. But you want to have a feeling about the layout of the chemical space. And the layout of the chemical space didn't look great in our case. So green is hope, and in our case, it always means product, and yellow is the limiting starting material, and everything else is stuff you don't want to have, so side products and other things. And as you can see, in most cases, hardly any conversion, maybe a little bit in toluene, maybe a little bit with copper oxide, copper acetate, potassium acetate, but not that much. But of course, one thing is grayed out, and in this case, the Wildcat TFE turned out to be turned out to be the winner. And of course, that was like 4 years ago, at the time when the whole thing with PFAS was not that much of an issue. But even back then, people didn't like the idea of running reactions in pure TFE. And so, we had to come up with better solutions. But in principle, you can see here there are some pretty nice hits of TFE with copper acetate, potassium acetate, and then you see product and you see the deprotected product, which, deprotection would anyway be the next step we didn't care that much about. So, see already quite a lot of product, but you also see that not everything is nice in here. So really some work left to be done. How do you then continue? Second plate, it's like, okay, can we somehow get away from stoichiometric copper as an oxidant? Either reoxidizing it with NMO or magnesium manganese dioxide, or like whatever other stuff that can stick. And nature gave us the answer. And it was basically, first of all, a stoichiometric oxidant is important. And second of all, some measure of fluorinated solvent is also important. And you can see that you can replace pure TFE with hexafluoroisopropanol. You would say that this is not really progress because you just replaced 3 fluorines with 6, but it turns out that you can also reduce that even further on the next plate. And you can also see how you can iterate your way forward, and then all of a sudden a reaction that didn't look so great now all of a sudden isn't so bad. And you see here in the final or somewhat final reaction conditions, you have a mixture of toluene with 10 equivalents of HFIP in a mixture with copper acetate. And yes, of course, your supplier won't be super happy if you tell him that you need 150 kilos of copper acetate in the reactor and that all this needs to be filtered off and get rid of. But we produced more than 50 or so kilos of that compound using that process, and it just scaled up wonderfully despite being heterogeneous and like all the other questions that you might have. Yeah. So this is just as an entrance point what you can do with HTE if you're pressed for time, if you have really not much precedent, and how quickly you can get from something that doesn't look great to something that is at least doable for a first larger campaign. With that, I'm handing over to Vera.
So, yeah, thank you. I hope you can hear me well. Otherwise, let me know. So you might wonder by now, like, how does the plate design and all these pie charts actually evolve and come together? And that's why we wanted to quickly show you our workflow, basically how we are set up in the lab and the data flow. So in blue, you see more how our data flow kind of embraces the whole yellow part, which is the robots in the lab. So we would start with an ELN, as you all have. Currently, we are with those dogmatics, where we really only draw the scheme with the expected product and side products. And from that one, we go into our Google Sheet. In the Google Sheet, we plan the whole reaction. So the scale, we have all the batches of the material in there. We plan at which temperature and dilution we want to run the plates. And the Google Sheet provides all the input files we need to have in the lab. So from p-touch labels to the robot input files and so on. So we would then do really rigorous solid dosing. So we try to avoid stock solutions wherever possible. So we would solid dose all the solids we have, 2 glove boxes, currently one for the newer robot you see here with Labman. Then the Chronic Quantos, where we started 6 years ago with that one still running well. After the solid dosing, the plate is closed by a human actually, brought to the different glove box where we handle all the liquids. And here we would have liquid handlers, as you see, Mantis, but also the Junior we have. However, we actually do that a lot by hand. And maybe it makes sense to you now when you see the times, how we estimate how much time we actually use per pillar. And for sure, we could automate the liquid dosing fully, but that actually takes then longer than when doing it by hand. So this is a hassle. It's a trade-off you have to think about when you automate stuff. Do you want to have it automated for the sake of automation, or do you want to have the throughput? And so far for us, it really comes down to still going with the multi-channel pipettes or with the Eppendorf multipet. So we would add all the liquid reagents and the solvents. Execution of the plate is then done on the junior, where we heat, stir. We can also shake and cool, of course. We take the in-process controls. Since we have in every reaction an internal standard, we take several samples per plate. So not only just an overnight quench sample, but we try to have at least 2, mostly 3 samples per plate to actually also get some information about kinetics or stability of the starting materials and products. Everything is run on LCMS. Then the whole interpretation and analysis we do in Spotfire. Some of you might know. Also, the report, since Roche is very much still in the Google environment, so far we do everything in Google Slides. So our customers get Google Slide presentations back with all the visualizations we just copy paste from Spotfire. And with that workflow, you see with the arrows, either you see after the Spotfire interpretation, it needs a second round, a second plate, or you can then go into a small scale up. For us, really the mantra is we want to standardize. That means also we need to compromise. So every reaction comes down to some solid dosing and some liquid dosing, and we want to run every reaction with that. You realize it does need compromises. For instance, feed control dosings, that's not possible in our setup so far. Or if you look at the analysis we do, it's only LCMS, right? And sometimes it's hard to tell if you really made the right product, the right regioisomer. Also, we run every sample on a 2-minute method. And as I already mentioned, we have 3 samples per 96-well plate. Comes down to many minutes. So we don't want to have methods optimized per reaction and then ending up with having 4-minute or 3-minute methods with perfect peak shape. So we much rather have a short method. Sometimes peak shape is not what analytical chemists would like to have, but we are synthetic chemists at heart, so we often just go with it. If you want to have a really deep dive in how the Google Sheet works, we have linked here our publication already 2 years ago, or there is also a pretty short YouTube video where we go through the Google Sheet and everything. But this is quite dry, so let's go back to chemistry, since all of you, I guess, are here because we have cool examples. And we brought here a real example we got also from a customer where they asked us, have you ever done direct arylation of this kind of diisopropylmalonate? And we checked in our data and realized, no, we actually never tried this, but we were also a bit puzzled, like, what do you want to do with a diisopropylmalonate on it? So it's kind of obvious that you further grow on this molecule. We thought the most obvious is that they want to build up the barbiturate on it. And since it's well known, barbiturates have very good pharmacologically impact. These drugs, hopefully you don't take them. We were actually asking back, are you interested in having a direct arylation on this barbituric acid? And turns out they were. So we checked literature. There was very, very little precedent. So we were a bit puzzled, like, how can that be? Since this moiety seems to be quite well known and also on the market. But the only thing we could find was this example here, where it was a derivative of the barbituric acid. They run it with X-phos in cesium carbonate dioxin. Seems fair, right? So we were curious definitely to try this out. First things first, though, we did plan a first plate with the malonate. You see here on the y-axis that we go quite broad in the solvents and also in the bases we take, and then you have the freedom of 12 columns just trying out palladium pre-catalyst, but also we wanted to give copper a shot, right? And as you see, we do find nice product. It's actually quite good, but we were still surprised how selective this reaction is. So for copper, it wouldn't work at all with none of the copper we tested. And also, pretty obvious, you need to have the right ligand that it does something. Either it goes and then it goes pretty well, or it doesn't do anything. So our customer was quite happy with that result, but still there was this question of how can we do the direct correlation of the barbituric acid? And here we did the same plate design. It turns out it's a lot less green now. And also, surprisingly, only conditions with the potassium phosphate DMSO or cesium carbonate DMSO, these are for us more like the copper conditions. That's why we have them on there. But you see, copper also here doesn't react. But then with the table bread phos, seems like we almost have a foot in the door. You see the LCMS, peak shape, and also many other things are going on. But once you see a little bit of product, we hope that we can optimize there. That's what we did with the next plates, playing around with this DMSO and different bases, basically screening all the pre-catalysts we have. And it was nice to see that there is an island of green using DBU DMSO for this reaction. And you can see here it's significant product in there. So that was definitely a good start. Customer at this point was very happy. They would take it in the lab. Medchem is definitely happy enough with these kind of chromatograms. But for us, we figured, okay, we know by now there is not much in literature, and we also seem to have this reaction with actually medchem aryl bromide work on a barbituric acid. So and we use that as starting point to actually develop maybe a new methodology for this kind of reaction. So that's when we went to the shelf and tested just many other leftover starting materials we have from our customers because we wanted to make sure it's not just the one aryl bromide, which happens to work with the barbituric acid. And turns out some of them actually work very well. But also some they just wouldn't go. It's not too surprising for some of them, but for others, we were like, okay, this is a good start. And now we could actually do this in a sophisticated manner for a paper. So we would go further and actually test our real halides. Oh, here, just quickly for you to highlight for the next couple slides, you see a lot of these green ticks and the red crosses or even orange ticks. And this is how we evaluate them. So whenever we judge it's a majority of the peak in the chromatogram is product, it will give a green tick. When it's really just minor or traces of product found or nothing, then it will be something red. You see here with one of them, we also did a scale up just to see how well these conditions translate from 2 milligram scale up to a couple 100 milligram scale. And we were actually pretty happy with the yield achieved in that. So as I already mentioned, now it's really about testing more substrates and trying to understand the scope we could achieve. And yeah, we were pretty happy. Like the suspicions one with ortho substituted, we were not so surprised that they wouldn't go. But for others, for instance, it's protected aldehyde or even the B pin you see on the far down right-hand side, we were actually very surprised that this would work, that we would be faster with the CHR relation than actually the Suzuki. So that was pretty cool. And so that looked good for our real halides. So we wanted to bring in a bit more creativity in the heterocycles. And there, yeah, things start to be a bit more difficult, but still for us, it showed this reaction actually can be done on a various of different substrates. With that, we figured, okay, now hell breaks loose. We just try everything. Let's switch to the nucleophile. So don't go away from barbituric acid and just try what else would work. And yeah, here the plate didn't show too much green. We were happy about this diketone in row one working. So that was pretty good. Actually worked with many different pre-catalysts and different solvent-base combinations. What puzzled us also was this phydantoin. We were like, oh, this would be super cool if you can make a CC coupling here with palladium on phydantoin, because yeah, you wouldn't expect that to work. And this is good to be suspicious. And as I already mentioned, we only do LCMS, right? This guy here has the same mass as when you do the CH, so the CC coupling. Well, when we did scale up, we saw then in the NMR this was a CN one. You have to be careful when you only do LCM masses, right? Phytantoin was a failure then. So what else is for us as process chemists and for MECHEM actually interesting? And we came here to this methyl Meldrum's acid. This Meldrum's acid is also a nice door opener for your synthetic approaches, right? But the methyl Meldrum's acid, as you can see, doesn't give anything. So we were like, okay, this is surprising, but maybe it is the steric hindrance because of this methyl there. So Meldrum's acid, on a side note, why is that so interesting? You see here the most obvious things you can do. You can further alkylate, you can do the corresponding amides or esters and carboxylic acids, but you can also think of many more reactions you can build up, right? So you can go and build these bicycles with the lactam moiety in there, or you do ring expansion, or you can build heterocycles like these pyrimidines, or even the spice cycles with the imidazole moiety in it. And there we are full in the MECHEM area, right? These people, they love these moieties. So for us was definitely the next goal. Okay, it worked with the barbituric acid. How far away can Meldrum's acid be? This is how the plate looks like. So again, we threw all the palladium catalysts on it. By then, we actually gave up on the copper and really just tried to find sweet spots in bases and solvents. So from a process chemist point of view, I mean, it's nice that this reaction works, but maybe you don't want to use, again, DMI or Briege with cesium carbonate, because then the extraction is just going to be hard. So we optimized a bit further, and we came with pretty good results for a process chemist with potassium phosphate in methyl THF. So that was pretty good for us. But you also see how many of these other ligands just don't work at all, and how big the difference really is between aqueous potassium phosphate versus dry potassium phosphate. So this should really highlight also the power of HTE, that you do have the freedom on a 96 well plate to test things out, and only just a small handful of reactions, you never know if you optimize in the wrong direction. And here you just at least have a little bit more freedom and to try to find a hit and to optimize into a good area. You never know if it's the global maxima though. So for sure, same thing. We did this analysis with the Meldrum's acid through the different, let's say, real molecules on it. And we were quite happy to see that this is super similar to what we saw with the barbituric acid. Also for the heteroallyl halides, this looks quite good. Tendency is actually works even a little bit better than with the barbituric acid. And then also for the aryl halides, it is very similar. However, who was super, super conscious now of listening, realized, like, for instance, that isopropyl or also this orthomethoxy here with the chloro, they didn't work with the barbituric acid. However, with the Meldrum's acid, now we do a green tick. This is actually how the plate looks like for that one. So here. These auto substituents, sometimes you can overcome these issues there. So it doesn't mean, oh, auto substituent, anyhow, this is not going to work. If you do find the right condition, you make this reaction work. And I find this really astonishing to see how different the conditions are. Like, take this isopropyl, and here with potassium carbonate, THF, and the alphos, we have no product at all. However, with cesium carbonate, DMI, and table breadphos, it's actually a pretty good reaction, where it's the complete opposite for the ometoxy, where the top conditions would work actually quite well, and the lower one doesn't work at all. And also there, this is very nice to have in a HTE setup that you can vary your 12 different coupling reagents or coupling partners and have then still a variety of 8 different conditions. So you don't have to nail it down to one condition and do that on 96 because we would have lost potential hits for sure. And with that, I think we just published that now in beginning of March, so 3 weeks ago. If you want to have the full story on that with the barbiturate and the Meldrum's acid, feel free to have a spot in that article.
So now, unfortunately, the chemistry is over, and I'm going to bore you for the rest of the time with statistics and lots of other tidbits that may be of interest for you. So this is us. Actually, Felix, my oldest, is not part of Team Rosal, but he really wanted to be part of the team hike. So we are like 4 full-time FTEs. And then postdocs, we have students. We really like to collaborate also with academia because there's so much you can do with HTE. And remembering my PhD times, I wish I had this kind of equipment to browse through chemical space. So yeah, we really like to collaborate with people. We ran a lot of experiments already, a lot of plates, a lot of different screenings. We really get some feeling of what works and what doesn't work. And still see the numbers going up every year. People more and more want to do HTE. And we really also want to give back to the community. So what Vera did is like look at all the data that we had so far and prepared these cheat sheets where it's like, okay, if you have a Buchwald-Hartwig with different kind of substitution patterns, what should you use in terms of catalyst, base, solvent? If you see certain side reactions, what should you do? What kind of catalyst should you buy? What kind of pre-catalysts are good? What aqueous bases should you use? Like all the stuff that throws off a lot of reactions that people try in the lab, and it's just unnecessary, to waste your time with stuff like. So I hope there are no palladium tetrakis fans, but like for example, there's just no point using palladium tetrakis anymore. It's just most of the time it just goes gray and bad, and then people will have a false negative. And then we have on the flip side, we have the same for Suzuki's. We have also some experience on CO couplings. There's more than Hatu out there, especially for Metchem. They are surprised that there are other coupling reagents. Not just kidding, but like we quite often get amide coupling requests, and the only problem there is that Hatu is not strong enough to activate the carboxylic acid, and the not very nucleophilic amine just doesn't cut it, just can't do the reaction. And so, we try to make them aware of other stuff and what works in our hands. Ullmann reactions, for the brave ones, if they want to try them, we also have some advice there. But in general, we suggest, going directly to screening because, there are just so many little things that can go wrong. And so this is one thing. We printed that, laminated that, and everybody who wants one can have that on their desk. And it not only takes away work from us because the success rate in the lab goes up, but also we hope that it clears out a little bit of the mystery of chemistry. But we also want to benefit from our data. And we want to benefit it in other ways than just remembering last week's Suzuki and using the same catalysts all over again, because in our short-term memory, DTPPF turned out to be a great ligand. So how can we make that large body of work useful for us so that we can actually design better plates? And you can see here, this pie chart shows you our landscape. Buchwald, Hartwig, and Suzuki's, they really dominate the landscape still, but we have a long, long tail of reactions, of things that people want to screen with us. And so we ideally the method should not only apply for Buchwald, Hartwig, and Suzuki, so basically machine learning here, where you need lots and lots of examples, but ideally it should also help us design plates for things that are not so common. And so we were looking for something that can bridge that gap between different substrate pairs, even though in most cases we don't have actual isolated yields, because for our medicinal chemistry colleagues especially, they will almost never have a product reference. I mean, the only reason why they come to us is because they don't have product, so we don't have anything to compare against. And so how can we find good starting points that are simple, interpretable, and less biased, where you don't always screen the same catalysts, bases, and solvents. And for that, we went to, we for a long time already had a look at Z-scores for racemate cleavages. There's this publication from BMS that really sparked our imagination, where they say like, okay, we use a tool called Z-scores from statistics. And this Z-score basically says, okay, I have this blue distribution here of all reaction results for a given plate. And then for each catalyst, for each solvent, for each base, I look at the individual subdistributions, and catalysts that have a distribution off here to the right, they are better than catalysts that are back here to the left, because overall the yield is better, and especially at the top N hits, they will turn out to be especially good. And so this dimensionless Z-score basically tells you how good a given reagent, catalyst, or combination of the two is relative to everything else that was present on that plate. And since it's dimensionless, you can now bridge all kinds of reactions, because a catalyst that turned out to be really good in one reaction and somewhat medium in another, all of a sudden you have a distribution of results, and you can actually do evaluations on that. So just to give you an example, you have a Suzuki coupling, and you have for the first reaction, you have only one hit with 50%, nothing else works. Still, although it's only 50% area, this will have a high Z-score. On the second plate, you will have many hits. It's an easy reaction. Everything works, but everything will have a relatively low Z-score because nothing really stands out. And for us, it's important that we kind of reward catalysts that work when nothing else works. We don't hang ourselves up on the absolute number here. We really want to have something that is better than other stuff, and that should shine. And this is also something that you need to keep in mind, because there are some caveats to take into account. One is selection bias. So almost all of our molecules come from customers that failed to run the reaction using standard conditions. So it's only a subset of the whole chemical space. Typically, the molecules are quite complicated, and we have no control over the molecules that people come to us with. So if one project decides to swamp us with 20 molecules that all look very similar, this will bias the whole distribution in the database and will lead us to choose catalysts or bases in the future that work good on this subset of molecules. So you really have to be careful with that. But in the end, this is what we can work with, and we try to make the best out of it. And here's a little case study. So looking at secondary aliphatic amines that react with aryl bromides or chlorides. You see, here are the best catalysts. You see here this dimethyl isoheptyl chlorocarbene is actually a catalyst that shows up again and again and again as a very heavy hitter. Better in many cases than the standard Buchwald biaryl type ligands. And you also see how our old thinking influences us or influenced us a lot over the time, because initially we followed the literature, and there QFOS is regarded as the gold standard of doing things, together with RUFOS. And so, we used this for a long time, again and again and again. But only over time we found out that actually the chlorocarbon for our substrates is better. And so you can see here, it makes really a big difference which catalysts I use. Here, over there, are the best bases and solvents. And you see the usual suspect, sodium T-butoxide, as a strong base with somewhat apolar solvents is good. But quickly below, you see that weaker bases show up. And, this is also due to our substrates. Many of the substrates that we receive will be quite sensitive. And although sodium T-butoxide may be the best base overall, that doesn't help you at all if the base actually kills your substrate. And so, weaker bases all of a sudden also show up and shine. But overall, you also see that the difference between the best base and the worst base is not that much. And it really shows you what a lot of people already would assume based on their experience. For Buckwald heart mix, the ligands really are the most important thing. You really want to be right with the ligand. If you're right with the ligand, choice of base, won't shift the picture too much anymore. So now you will think, what does that help me? And you would be right, except for we have actually published the whole thing. And so you can go to, I'll show you the link afterwards. You can go to go.roche.com Z-score app, actually load. Then you are here, and then you see here, let's see a Suzuki. And we want to have a Suzuki with an aryl boronic acid. It can also be an ester or an trifluoroborate. And we want to combine it with an aryl bromide or also an aryl chloride. And we are interested in finding the best ligand. And then, yeah. And then you see, okay, Cataxim is good, DTPPF is good, Amphos is good, tritibutylphosphine is good. The usual suspects. If you then say, maybe I'm interested in the best base or the best base and solvent combination, now you know, okay, potassium hydroxide toluene is good. If you then want to know, oh, do you guys use water as an additive or as a solvent? Then you see that here, and you see immediately, what reaction that was, what the hit is based on, what the exact conditions are. And it's, for us, it's really, really useful because we are very much using shotguns when designing plates, right? We don't care really about the best catalyst. For us, the best 8 catalysts are interesting, or the best say 12 solvent-based combinations. For that, it allows you really to browse the chemical space very quickly. You can also do interesting other stuff, like which cross combinations are really the best, like violent charts. The student, Jesse, who built that, really had a lot of fun vibe coding the whole application together. And you can use that all for free. And you can also download the source code, of course. And you can here on ACS Central Science read everything about it. You can even up here upload your own data set. So if you want to analyze your own data and produce it in the format that is required for this, you can do it as well. So back to the presentation and finished with the infomercial. So now, we absolutely love HTE. We use the results all the time, also for our own projects. But you have to keep in mind certain things when you work with HTE results. Our environment is we work in a glove box and we work on milligram scale. And there are important consequences that you may not think of when you transfer these results to the lab. So we are inert and dry. That means our cesium carbonate is also dry. It is not lumpy and it doesn't, like almost melt away when you open the bottle. And this can make a huge difference. When we steer on milligram scale, our steering is as close to perfect as you can get. And also we see a lot of grinding. So when you have heterogeneous reaction conditions like cesium carbonate in toluene, where you really have not much base solubility, you have to keep that in mind because that may work on 2 milligram scale, but on the lab it may totally fail. We mostly work on small scale with very little solvent. And because our customers typically only want to do a reaction once, they're only interested in 50 milligrams of the product. Instead of transferring the results to the lab, we will just do a quick scale up for them. And instead of scaling it up, we just replicate the screening hit 50 times on a 96 well plate to just get the product. Like what point is doing process research for a reaction that will only be run once? But when you want to scale it up, like be aware of heterogeneous reaction conditions, make sure that you understand what you're doing. Adding a little bit of water can really help. If you start with a messy HTE hit, don't expect it just by Easter miracle to clear up all of a sudden, and it will typically get messier. If you have an aqueous base, it's not the same as throwing base in and adding some water. Degassing and reagent quality is often important, and very often the catalyst loading that we use, because we are anyway at small amounts, is way too high. So often it can be reduced significantly. And with that, some acknowledgement. Just like children, HTE can also be raised by it needs a whole village to raise to get HTE results. And so we have lots of support from lots of different people. And without it, all that would not be possible. And for us, it's really important to give you some messages. I mean, we make it as easy as possible for people to reach us and to get to us, to give us work. Because whatever form that you let them fill out will just increase the resistance, and we don't like that. We want to be as relevant as possible. A good HTE result for a medchem chemist is not the same as for a process chemist. We want to be fast, especially for medchem. If it's more than 3 days, it kind of becomes stale. And it should be super, super useful for future screens. We really try to avoid mistakes. We really try to get the most out of the screening results, because who knows what similar reactions may be in store for us in the future. And finally, we will not have a job without customers. This is really important. If we are not useful for the people in the labs, they will not come back, and at some point, the whole HTE dream will be over. And with that, thank you very much for your attention. And shoot, we are open for questions.
Thank you, George and Vera. It was a really great presentation, really insightful. If anyone does have a question, please feel free to put it into the chat. You'll also see it on your screen that we have a poll. And as I said at the beginning, the Process Chemistry and Technology Group is organised by volunteers, and we would appreciate some input into what kind of topics you would like for our future webinars. But we already do have some questions. One of the first ones was, how can the participants get a physical copy of the cheat sheets?
Oh, a physical copy.
Or perhaps download a cheat sheet if that's easier.
Yeah, so we can include the cheat sheet with the presentation as a PDF, and then you can print it.
That would be great. Thank you.
Okay. How do you take multiple samples when the reaction is heated? Yeah, that's maybe you want to answer.
So we would effectively taking it from the heat, wait a little bit, and then open it, and then putting it back. But everything kept in the glove box, right? So It is inert. So far, we don't see that we kill the reaction with that or that we stall reactions because of that. When you heat them back up, it seems to be fine. Of course, you need to wait a bit longer when it's 110 degrees rather than when it's just 60 degrees.
And I should say that also we do not pierce the lid,
Yeah.
because if you do that 3 times, there's not much left in terms of solvent and stuff, typically. Okay, what equipment did you find absolutely essential for good HTE? Which one can be left for a later day? I think we have very similar opinions about that.
It's definitely the solid dosing, right? Think about the liquid dosing later. We thought in the beginning we would handle the liquid dosing completely different than what we saw then actually in real life. So go for a good solid dosing solution for you, and then the liquid dosing you can survive with doing that manually for a while.
And they do get cheaper. You don't need to have the super expensive Quantas, but of course, with price also comes some additional features and stuff. Um, Solid dosing and liquid. Scale up scores on some of the slide. I don't know this.
Yeah, maybe that's for the Meldrums and barbituric acid slides. So the scale up, it was really a scale up. I think our bachelor student did that on 1 gram scale and then had isolated yield uh, and characterized by NMR, and that's done.
Yeah, and this what you think is a score, I think, is just the peak area percent. We
Yeah.
have the peak area percent from screening, peak area percent from scale up, and then the isolated yield from scale up to somehow link these three together. Did you observe big difference between solid and liquid dosing? Um, we don't have much experience there because we don't do much automate like robotic liquid dosing so far. Um,
I think from a user perspective, handling a pretty sophisticated liquid handler takes a lot more of super user knowledge than dealing with a solid dosing robot, because the solid dosing robots, they just dose solid. They can't really do much else. Whereas liquid dosings, you have to wash the needles or think about the disposable needles or like source plates. So how do you provide the solvents on the platform to go into the plate? So there, I feel like the super user level needs to be higher. Yeah.
so, do you okay, so a tool for further analyze electrophiles. Um, no, actually, maybe we should have. Maybe we should have followed up on that, but so far we haven't. We kind of accepted our fate there and just, you know, and you see some of the stuff is really puzzling. If you look at the results, s- very similar substrates can either work or completely fail, and I think it will be very hard to kind of replicate these super steep gradients in any kind of prediction model. Maybe I'm wrong, but I'm this bit pessimistic there. Um, 1 to 3 milligrams. How do you make sure? Yeah, so the actual dispense. So we actually measure how much is in there. So we read back all the log files, and if dosing is really too low, then we will go back and say like, okay, top up and add some more. But in the end, in our Spotfire tool, we have the real amounts in there. And if it's plus minus, say 10, 15, 20%, sometimes we live with that and accept it. Yeah. So speed. Photochemistry, yeah, photoredox is being dealt with in a different lab. And process chemistry, so far not much photoredox has arrived that we could not circumvent using different normal chemistry. And so, yeah, this is that. But I think it's cool technology. It's just not so easy to scale up in many cases. That link, I don't doesn't look like a question. So reactions with heterogeneous superstoichiometric reductants. Yeah, that is tricky. It is true, especially with, say, in situ Suzuki's or Negishis. Um, we typically try to screen different particle size distributions, say of zinc, and try to somehow get a grips on that. but we have seen in the past that that there were surprises for cross-electrified couplings. That stuff that worked for us reliably in the lab didn't work so well. We did, however, see that we're using surfactants. We could sometimes mitigate that and bridge the gap, get stuff to work that wouldn't work. So, um, reform behind alphas. Yes. So, uh, no. Um, because we try to, we have already 500 or 600 dosing heads. And so if we now had another set of palladium precursors and ligands as dosing heads, our glove box and our heads would explode probably. And so we say like, okay, we only screen pre-catalysts. And if the lab then wants to make the step away from the pre-catalyst to, say, palladium DBA, palladium acetate plus the ligand, and do in situ activation, they can do that, but we are not equipped.
There is also a lab after us in process development, right? Who is doing then also HTE looking exactly into this, like trying to find the cheapest possible ligand, and they will deal with it.
Yeah, we're the cowboys. Um, so
Copper chemistry.
copper chemistry, yes. This is a dream. We haven't tested them. We have the Hartwig, the Buchwald ligands. So far not super successful, but if there were a copper pre-catalyst, we would definitely want to use them because one of the things that don't dose super well are these copper salts, especially copper oxide. Not great.
Then they are heavy and you have a lot of it always in there. So with the palladium pre-catalyst, we are perfectly fine with being in the 8 mole percent of the catalyst, aiming for 2 milligrams. But then with the copper to come on a 2 milligram for that it's convenient for the robot to dose, we are at 20 mole or 30 mole percent, which means you have to have 40 mole percent of the ligand on it, and then it's just a lot.
Well, often do you take the potential scale-up of a reaction into account before? So, um, so when we get a request from process, we always take that into account, but we allow us some creative liberty when designing the plate. So we will also put solvents or catalysts on there that may not be super scale-up friendly, but if we anticipate the reaction to be hard, we want to at least have something for the customer. So, we try to build a core around something process friendly, but then also, explore a little bit around it. And then for the follow-up plates, hopefully we can go in a direction that works for the customer. Um,
Think about the frustrating or the customers being frustrated about the scale up thing. That's why we decided to split scale ups, right? Because in the beginning, we definitely did run into the case where we would have a good hit for 2 milligrams, but then for 15 or 50 milligrams, nothing at all. So expectation management, you definitely have to do when you send out the results. And also when we find conditions where we know this catalyst is just very, very air sensitive. Like we tell them, like you have to do it in the glove box for you. For mechan people, they're happy with that for sure. For PCMC process research, we'll have to optimize further until we would say this is ready for a scale up in the lab.
Also, often what we see is we have here the inertness of the HT lab, super inert. Then you go to the first scale up in the lab, it kind of drops. And then once you're back in the plant, then all of a sudden inertness doesn't have much of a problem anymore. So you kind of have to survive this first phase in the lab. And we also by now know what kind of stuff has problems in scale up, especially heterogeneous inorganic bases, are notorious. And so we know that, for example, cesium carbonate toluene is just no good way of doing screenings for scale up. You want to have something like cesium carbonate in T-amyl alcohol, or at least some alcohol component to increase solubility, and then all of a sudden your scale up will be a lot better. Okay, so the palladium ligand we already answered. Um, Yes. So this is an area percent product, but with a little tweak to it. It's area percent product and then renormalized by throwing away everything that is not product or starting material related. We throw away area percent of, say, solvent or ligand or internal standard so that it's somewhat comparable between different vials. Because if you have one column that has toluene in there, then all your area percents all of a sudden drop. So we want to have that somewhat comparable. Yes.
I think there's one last question. Yeah, on the chem beads for solid dosing. Have you experienced those?
So maybe just the last thing with the 10%, that is very true. We have a filter, and I think it's 10 or 15% of area percent. And if there's nothing on the plate above 15% or so, then the whole plate is discarded for the analysis. That's why it's only 77,000 instead of 125,000 reactions. Not everything, makes it and has actually any positive result. So that's how we want to protect ourselves. Chem beads, you have some experience.
Yeah, I mean, we don't use them for a daily business. We know from our HTE colleagues who use them also for process research and say there is absolutely no issue with then scaling up and going from shaking to steering and so on. But for us, it worked without. Our group in MedChem, though, they use chem beads for their late stage functionalization HTE platform. But there they have built their own dispenser, and I think that's then the way to go because that's super fast dispensing, and you can cut on the dispensing time a lot there. So when you want to go with chem beads, I would recommend go then also for a different dispensing. It works with the Quantos heads, but still you can cut on the dispensing once you have a good coating on that beads.
Cool.
That's great. I think you managed to get through all of the questions, which is fantastic, and a lot of questions, which I think reflects the quality of the presentation and how much everyone engaged with it. Thank you so much for being our speakers today. Really appreciate it. And thank you again to everyone who joined today. Please check out our LinkedIn page, and also you can find the Process Chemistry and Technology events on the Royal Society of Chemistry page. We have a webinar every month on the last Tuesday, so check out what's coming up next month. So thanks again, everyone. I hope you have a great rest of the day. Thanks for joining.
Thank you. Have a good one. Bye-bye.
Bye.